In the last lecture, we looked at the addition rule for probability. Now we're going to look at the multiplication rule for probability, and along with this rule, we'll look at concepts such as conditional probability, independent events, and the confusion of the inverse. So let's get started. All right, so say you're given this test, and it only has these two questions. True or false, Cinco de Mayo celebrates Mexico's victory over the French army in this battle. And the second question is, when did British Honduras first attain full internal self-government? So the answer to this is true, and the answer to this is 1964, C. Now, if let's suppose you didn't study and you're going to guess, well, what is the probability that they would get both correct just by randomly picking true or false and then from A to E? Well, one approach would be to list out the sample space. In this case, the sample space is fairly small. And so we can determine the cardinality. We can count the number of elements in this set easily enough. As you can see, we have 10 elements in this set. There is only one of them that corresponds to both being correct. And so the probability is 1 out of 10. Note that in this case, when we talk about the probability of T and C, we're talking about two events. And so let's take a look at this definition here. The probability of A and B, where A and B are two events, is a probability that A occurs in some first trial and B then occurs in some second trial. Be aware that sometimes this very same expression here can be referring to two events which occur in the same trial. And so you need to be able to differentiate between those from the context you're given. As we move along, we'll be encountering problems where the sample space is just too enormous to list. And so in those cases, then you'll have to find ways to be able to count, to determine the size, the cardinality of the sample space without actually listing them. So as you're beginning to see, this notion of counting combinatorics is crucial, and we'll be looking at that in the very near future. Another way to approach this problem is to create what is called a tree diagram. And so in the tree diagram, we represent what happens in the first trial. You can either pick true or false. Notice you have two choices. And then for each of these, you have 5 choices, A to E. And so if you come along here, this is T, true, and then you pick A, true, and then you pick B, true, and then you pick C. And all the way down to false, you pick D, false, you pick E. So notice you have 10 options at the end here, and the only correct one is this one. That is 1 out of 10. So both these approaches, creating the sample space and using a tree diagram, both of these are not very effective tools when dealing with serious problems. These are only used so that you can get an idea. Sometimes when you're dealing with a more complex problem, you can kind of draw a tree diagram just to kind of get a sense of it, but of course you will not be able to draw a complete tree diagram. Likewise, sometimes you might just list the sample space, a few elements in it, just to get an idea of what the elements in the sample space would look like. But no, you would not be able to list all the elements, and you would not be able to draw a complete tree diagram. So what is going to become very important then is that you learn more sophisticated ways of counting. Here, once again, we're dealing with the results from tests for marijuana use. In this case, you're asked that if you were to select 2 subjects from this group of 300 without replacement. So let's get clear what that means. It means that when you pick somebody for your second choice, the first person you picked can't be picked again. If the situation was with replacement, then you could pick the same person twice. So they want you to find the probability that the first person selected had a positive test result and that the second person selected had a negative test result. So let's take a look at the first selection. What's the probability that a person selected at random has a positive test result? Well, we have 143 people here, and so the probability then is 143 out of 300. Now we want to find the probability that the second person selected has a negative test result. Notice one person has been removed from the group, so it's no longer 300 people. It's 299 people that you have to pick from. And of course, since the first person chosen has a positive test result, well, you still have 157 people with negative test results. And so it's going to be 157 out of 299, not 300. And so the probability then is 143 over 300 times 157 over 299, giving 0.250. So notice this is a situation involving and. We want to find the probability that the first person selected had a positive test result and the second person selected had a negative test result. However, we can't just say 143 over 300 times 157 over 300. The probability of the second event has to be calculated in such a way as to take into account what happened as a result of the outcome of the first event. So when you select without replacement, the second probability has to take into account the fact that the first selection removed one of the subjects from the group. And so you only have 299 subjects available for the second selection. So this introduces us then to the concept of a conditional probability. If you're wondering where this multiplication came from, let's take a look back here. If we look at the event of picking true or false, the probability of picking true is 1/2. So this would be equal to the probability of picking true times the probability of picking C. What's the probability of picking true? We just said it's 1/2. We see it right here. And here, once you have picked true, what's the probability of picking C? So once you have picked true, what's the probability of picking C? Well, then that's 1/5. And that's why we multiply these two values here. And so we get 1/10. And so when we want to find the probability of A and B, it's the probability of A times the probability of B, assuming that B is in no way dependent on what occurred in A. So the act of picking one of these is in no way affected by whether or not you pick true or false. Notice, if you pick true, it's A, B, C, D, E. If you pick false, it's A, B, C, D, E. Now, if there was a difference, like if you picked false, you only could pick A, B, and C, and if you pick true, you had to pick from C, D, and E, then that would make things a bit different, because then the second event would depend on the outcome of the first event. So that's not the case here. So these events, picking true or false, picking from A to E, these are said to be independent events. Here now, picking a positive test result, and then in the second event, picking a negative test result, these are not independent events, right? The outcome of the probability of the second event depends on the outcome of the first event. So notice that's why we had to go 143 times 300. Sorry, 143 divided by 300 times 157 divided by 299, and then not 300. So in fact, what we have here is a conditional probability. The probability of this event depends on the outcome of the first event. Let's say we have two events. We have the event A, and this is some event B. So this is, our little Venn diagram here. And again, everything here is our sample space, otherwise known as the universal set. All right, so when we talk about the probability of B given that A occurs, well, it's a probability of this event occurring given that this one has occurred. And so this is what conditional probability is all about. So as it says here, the probability of B occurring given that A has occurred represents the probability of event B occurring after it is assumed that event A has already occurred. Two events are said to be independent if the occurrence of one does not affect the probability of the occurrence of the other. And so we'll be looking at this very closely as we continue to understand conditional probability and then use our understanding of conditional probability and independent events to finally get our multiplication rule. So here are two examples. If you're looking for independent events, we can say winning the Bolido and winning Lotto, right? They are independent. Dependent events would be, for example, having your car start and making it to work on time. You are less likely to make it to work on time if your car doesn't start. So I think these are two good examples here. And here we are finally at the multiplication rule. The probability of A and B is the probability of A times the probability of B given that A occurred. So this equation is implying that the events are not independent, that the probability of B is somehow affected by the occurrence of A. Now, if the events are in fact independent, well, it means then that the events, B does not depend on A at all, in which case then this would reduce to this. The probability of B given that A occurred is simply the probability of B because it doesn't depend on whether A occurred or not. So that's what this is saying here, right? If the events are independent, then the probability of A and B is simply the probability of A times the probability of B. And if they are not independent, then the probability of A and B is the probability of A times the probability of B, given that A occurred. Note this can also be written another way. I can say the probability, and I'll use this notation, is the probability of A given that B occurred times the probability of B. And again, and once more, if the events are independent, then the probability of A given that B occurred is simply the probability of A. In either case, if the events are independent, we end up with this. So here the focus is on finding the probability of A and B, but later on we'll be focusing more on this, the conditional probability, the probability of A given that B occurred, or the probability of B given that A occurred. Let's apply the rule using this example. A biologist experiments with a sample of 2 vascular plants, denoted here by V, and 4 non-vascular plants, denoted here by N. Listed below are the codes for the 6 plants being studied. She wants to randomly select 2 of the plants for further experimentation. Find the probability that the first selected plant is non-vascular and the second plant is also non-vascular. Assume that the selections are made A with replacement and B without replacement. So you should by now recognize that if we carry out this with replacement, then the 2 selections will be independent. It won't matter which selection she made, which choice she made in the first selection. However, if it's done without replacement, then it will matter what selections she made. So let's take a look at this. If the 2 plants are selected with replacement, the 2 selections are independent. And so what's the probability of picking a non-vascular plant the first time and picking a non-vascular plant the second time? It's 4 over 6 times 4 over 6. And that's that. You get 0.444. However, if it's done without replacement, we're going to find that we get a different answer, because in the first case here, what's the probability of the first plant being non-vascular? Well, it's 4 out of 6. And what's the probability of the second plant being non-vascular? If we assume the first event occurred, then one of these non-vascular plants has been removed. And so now there are only 3 remaining. So it's 3 out of a total of 5, not 6. So see what's occurring here. So this is the probability then of the second plant being non-vascular, given that the first plant chosen was non-vascular. So make sure you see this. And of course the answer is 0.4. A geneticist develops a procedure for increasing the likelihood of female babies. In an initial test, 20 couples use the method and the results consist of 20 females among 20 babies. Assuming that the gender selection process has no effect. Let's read this again. Assuming, note there's an assumption here. Assuming that the gender selection procedure has no effect, find the probability of getting 20 females among 20 babies by chance. Based on the result, is there strong evidence to support the geneticist's claim that the procedure is effective in increasing the likelihood that babies will be females? So here we have an assumption, and based on this assumption, we want to see, well, what is the likelihood of some observed phenomenon? If the likelihood of that observed phenomenon is very, very small, extremely small, then we're going to reject that assumption. So let's continue here. Essentially, what we're looking for is the probability that all these offspring are going to be female. That is the probability that the first is female and the second is female and the third is female, all the way up to 20. So here you begin to see the need for some mathematical knowledge. You do not want to write 0.5 times 0.5 times 0.5. You should recognize that it's 20 of these, so it's 0.5 to the 20th power, and you should not have to go 0.5, 0.5, 0.5 in your calculator. You just say 0.5 to the 20th power, and this is your answer. Very, very small probability. So it is very unlikely that 20 couples would have 20 female babies just by chance. So based on this, then it would be wise to reject the assumption that the gender selection procedure has no effect. Of course, if you reject this assumption, it means then that you are accepting that this gender selection procedure does have an effect. The idea of at least one can be very useful at times. So let's look at a very simple problem here. Find the probability of a couple having at least one girl among 3 children. Assume that boys and girls are equally likely and that the gender of a child is independent of the gender of any brothers or sisters. So let's say A is the event of having at least one girl among 3 children. Well, we can find the probability of event A by first finding the probability of the complement of A, and then make use of the fact that the probability of A is 1 minus the probability of the complement of A. And so what's the probability of the complement of A? Well, the complement of A is having all boys, right? If you don't have at least one girl, the only way you can do that is to have no girls, which means then that you have all boys. So if you're looking to find the probability of having at least one girl, one way to do this would be to find the probability of having 3 boys, which is the complement of this event. The probability of having 3 boys is 1/2 times 1/2 times 1/2. Again, note that these are independent events, so we can just multiply across like this. And then the probability of having at least one girl is going to be 1 minus this. And so it's going to be 1 minus 1/8, which is then 7/8. So this is a useful thing to remember. To find the probability of at least one of something, calculate the probability of none, then subtract that result from 1. That is, the probability of at least one is equal to 1 minus the probability of none. And now for a second and more profound look at conditional probability. Here we have 2 equations. Here is the probability of B given A, and here we have the probability of A given B. A very useful way to think about conditional probability is to look at it using this Venn diagram here. So normally the probability of A would be the cardinality of the set A, the number of elements in the set A, divided by the number of elements in the entire sample space. However, since it's being assumed that the event B has occurred, well, then we are only interested in the elements in A that are also in B. So the probability then of A, given that B has occurred, will be the number of elements in the intersection, in other words, the number of elements in A that are also in B, divided by the number of elements in B. So let's look at an example. We return to this situation here of the results of the tests for marijuana use. So in this case, they're asking if one of the 300 test subjects is randomly selected, find the probability that the person tested positive, given that he or she actually used marijuana. Note, if the question had simply asked, find the probability that the person tested positive, it would simply be what? 119 plus 24, that's 143. That would be 143 divided by 300. But now we have this little phrase here, given that he or she actually used marijuana, which means then now that we can't divide by the entire 300 because we are only focused on those who use the marijuana, and that's 122. So then, of those who actually used marijuana, how many got a positive test result? 119. So that's what we have here. The probability of testing positive given that you used marijuana is 119 divided by 22. We could look at it using the formula. The probability that someone used marijuana and tested positive is 119 out of 300. The probability that somebody used marijuana is 122 out of 300. And so you can see this will become 119 divided by 122. Let's look at this case here. If one of the 300 test subjects is randomly selected, find the probability that the person actually used marijuana, given that he or she tested positive. So this is what they're asking for now. A very common mistake is for people to think that the probability of testing positive, given that you use marijuana, is going to be the same as the probability that you use marijuana, given that you had a positive test. So here, if it's given that you had a positive result, then we have to look at the positives, and that's going to be these 143. Right? And of these 143, then, what's the probability that you used marijuana? 119. So it's 119 divided by 143. We could look at it using the formula, which says then that's the probability of having used marijuana and testing positive. Notice we get the same 119 over 300. But now the probability of testing positive is 143 divided by 300. Right? That's the sum of these two numbers here divided by 300. So this brings us to a very important idea, that the probability of A given B may be visualized as restricting the sample space to situations in which B occurs. The logic behind this equation is that if the possible outcomes for A and B are restricted to those in which B occurs, this set B serves as the new sample space. So we're looking for the cardinality of the intersection. That's what these things are here. 119 divided by the cardinality of B. So in this case, B is the event that you use marijuana, and in this case, B is the event that you test positive. We can use this Venn diagram to perhaps better understand what's going on here. We can say that A is in this case, that A is the event that you test positive and B is the event that you use marijuana. Well, you want the probability that you test positive given that you use marijuana. So then it's going to be this intersection here divided by all of this. And in this case, in the second case here, B, this becomes the event that you use marijuana and this becomes the event that you tested positive. So you have to find the intersection, those that use marijuana and tested positive, and divide that by the total number who tested positive. So note these are different. Here you get 0.975, here you get 0.832. Confusing these two, right? To somehow think that the probability of A given B is the same as the probability of B given A is called the confusion of the inverse. And it can pose very serious problems in different disciplines. Very careful decisions have to be made, both by the medical practitioner and the patient when it comes to serious illnesses like cancer. Not taking a treatment for not being treated for cancer can, of course, lead to dire results. It can have dire consequences. However, treating for cancer when you don't have cancer can also have dire consequences. The treatment for cancer is, as they say, nothing nice. So it is very important that physicians not confuse the probability of having cancer given that you have a positive test with the probability of getting a positive test given that you have cancer. And so this can be a serious problem, and this point that is being made here is taken from the medical literature, and I'll just read it out. It says about 95% of physicians estimated the probability of cancer given a positive test to be about 10 times too high, with the result that patients were given diagnoses that were very misleading and patients were unnecessarily distressed by the incorrect information. So sometimes when you look at the literature is talking about the probability of getting a positive test. So let's suppose a company is coming up with a test, and they might say the probability of this test detecting cancer, for example, a certain type of cancer, is, let's say, 99%. If you have cancer, this test will tell you that you have cancer 99% of the time. However, that is not the same as if you take a test and you get a positive result. What is the probability that you actually have cancer? So these are two very distinct issues, and we will not go into this in any more detail in this course, but as you can imagine, this is something very important. Okay, so I'll leave you all with this, and see you in the next one.